So hello everyone, good morning. My name is Thibault. I'm a second year PhD student with Selma. And I would like to convince you in my talk today that binary stars take what they get. And so we had a very nice introduction or explanation already this by Ilva yesterday. But if you want to understand the depths of stars, these interstellar black holes, we inevitably have to understand what went before them. So we need to understand the stellar interactions that lead up to these black holes. And the very first step in this binary interaction is this first step of mass transfer. And this has a huge effect on the final orbits and masses that go after this step. And because the first you expect this to be understood very well and not have many uncertainties. However, this is not the case. There's many different theories of how exactly this stable mass transfer works, but the two main ones are a thermally limited model that says that this accreting star cannot accrete too much too quickly. Otherwise, it expands, it leads to a common envelope or a merger, and it's no longer stable mass transfer. There's a second theory, that is this rotationally limited model, that says that, okay, once this donor star throws mass onto the companion star, this companion gains angular momentum very quickly. And this limits the mass transfer, and so you can do a pretty simple calculation that says stars should only be able to accrete a small percentage of this transferred mass. On the observation side, the important stars to try to constrain the stable mass transfer channel are these strip stars. And the problem with these strip stars is that they are very hard to find. If you don't believe me, you should ask Ilva. She'll convince you of that. And so far, there's about roughly 20 Wolf-Rayet O-star binaries that have been used to constrain mass transfer, and they find very non-conservative accretion, which confirms this rotationally limited model. However, there was this, up until a few years ago, this one subdwarf, this B star system, that accreted at least 50% of the transferred mass. And so this was in strong tension with these models, and we can ask, well, is this an outlier or the rule? And I'm sorry to spoil it, but I'm going to make this tension even worse. And so what is this subdwarf B star system? Well, this was 5%, which consists of a 1 solar mass strip star and a roughly 10 solar mass main sequence star. This strip star has lost its envelope, given it to the accretor, and this accretor is now spinning very quickly by gaining angular momentum and mass. And we don't know how much mass has then left the system that the accretor didn't keep. And these strip stars plus B binaries are key for understanding the stable mass transfer channel because we can be very sure that they have just undergone stable mass transfer. This is also by using their orbital periods. It's a very consistent and clear picture. And so we had this one system, and now we actually have a much larger sample of 16 similar systems. This is thanks to advances in spectroscopy and interferometry that allows us to get very constrained masses for these systems. So this is an interferometry image that was also shown by Hugh yesterday. And we actually are able to resolve in 3D the orbits of the subdwarf around the BE star. And if we can do that, we can get very precise mass estimates of these both components in the system. And if we have these precise dynamical masses, we can use that to infer information about the stable mass transfer channel and the initial states of the systems. And the way that we do that is as follows. So this is the methodology that Ono Pols did in 2007, but I'll briefly explain it now. So we know the present-day masses of the strip star and B star systems. If we want to infer the initial states, where they came from, we use our knowledge on single-star evolution that links the present-day helium core mass to the initial mass, because more massive stars lead to more massive helium cores at the end of the main sequence, which is when these stars have lost their envelope. And so we know the initial mass of the donor. Now, there's a free parameter here, which is the initial mass of the accretor and also the mass transfer efficiency. So in the conservative case, the accreting star kept all of the mass that the donor gave it. In the less conservative case, the accreting star did not keep all of the mass, and so it must have been more massive initially to explain the present-day mass of the BE star. And note that there's a fundamental evolutionary constraint here, where the donor star must have been more massive initially than the accreting star. Otherwise, the companion would have evolved faster, and it would have transferred mass in the other direction. This is not what happens. So we have this upper bound on the initial mass of the companion star, which means that in order to explain the present-day mass of the BE star, it must have accreted at least the difference. So we have this lower bound on the mass transfer process. And we can do this not just for phi Persei, as we did here. We can do this for all 16 systems in our sample. And we can also do this for actually any hypothetical combination of subdwarf mass and BE star mass, which is what I show in this figure. So on the x-axis, we have the mass of the strip star. On the y-axis, we have the mass of the accretor. The points with the arrow bars are the observed systems. And in the background, in color, I show our minimum bounds for the mass transfer efficiency. And so the first thing we see is that phi Persei in the middle here is not just an outlier, but it represents a larger population of systems. And even so, half the systems actually have stronger mass transfer efficiency constraints than phi Persei. And so this is a very strong result. And if we then convert this to the allowed ranges for mass transfer efficiency for each of our 16 systems, where we're bounded by below by our inferred lower bounds and bounded by above by a weak constraint on the initial mass ratio, and we compare this to predictions for the theoretical models, where at the top we'll see this rotationally limited model, which predicts a very non-conservative accretion, which is in tension with almost all of these systems. This is an option used in MESA and therefore also used in many binary population statistics codes, such as Poseidon and also grids by the Bond group. But this is in strong tension with the data. Then there's this thermally limited model that limits accretion to 10 times the thermal timescale, which predicts this bimodal distribution of either very non-conservative accretion or perfectly conservative accretion. But almost all of our systems lie in this range below, in between those, which is like 30 to 70% accretion, which is very little support for this model. So we also find tension there. And what's interesting is that a constant beta, which is often used as an approximation, actually fits all of these systems if we put it at like 0.7, let's say. And so we can discuss, well, how can stars accrete so much? And there's many different ideas. One is tides, but these systems are too far away for tides to have a strong effect. They could be magnetic fields, but these BE stars have not been detected to have strong magnetic fields. And so the most likely explanation is that there's some kind of viscous accretion disk that handles this angular momentum efficiently, while still allowing for mass to accrete onto the companion star. How this compares to other work is that we actually find support for such a high accretion efficiency from various similar works. So at lower mass, we find support. At an earlier stage, which was presented by Reese yesterday, we also find support, and a slightly higher mass in X-ray binaries, we find similar support. In contrast, at much higher mass, if you go to 40 to 60 solar masses, mass transfer is likely to be less efficient. This actually applies a mass dependence, where at low mass you have not much accretion, and at high mass you have very efficient, the opposite. Low mass has very good accretion, high mass, less efficient accretion. And this is actually also seen in hydro simulations by Peter Scherbach, for example, where if you bump up this mass transfer rate, this companion star cannot keep any of the mass. And so there's some more interesting work recently by Manos Sabartas with strip envelope supernovae that also seems to imply not very efficient accretion. And then there's some work with algols, Rikoshik, for example, but it's difficult to give strong statements about that. And so there's very strong implications for these results, specifically on stable mass transfer channel, where it affects the final masses and orbits. And if we look at gravitational waves, for example, changing this efficiency changes which progenitors form gravitational waves. And it not only changes which progenitors form gravitational waves, but also it affects the local merger rates for black hole neutron stars, and various other things. And so I'll end here by showing that we've found predominantly efficient mass transfer in the 2 to 10 solar mass range. And I'll leave you with this. This is a picture of Seneca in the companion star, because binary stars can kind of be seen as the original Stoics, in the sense that whatever life throws at them, they take what they get. Thank you.
It's for Thibault. Okay, here, hang on. I think that Niv was first.
Hi, thanks for the nice talk. So is there any relation between the orbital period of these systems and the conservativeness that you see today? And like, are these systems confidently have gone through like case B mass transfer so that you can map the current core mass to the original star's mass?
Right. If we take, on the last question, if we take a realistic amount of angular momentum loss, and we go back to the initial period of these systems, 14 of the 16 systems are consistent with case B. There's one that's likely case A, and another one that cannot be explained, as Anna Chiara Pico showed, which is HR 6819. But of 14 systems, we are confident that they're case B. And there is some correlation with the inferred initial period of the systems. So we see that if the initial periods of the systems are bigger, then there's less strong constraints on the mass transfer efficiency, which could imply a period dependence of this accretion. Yes.
Thank you. Great talk. I fully agree. I mean, it's fantastic that we're realizing this, and indeed in Poseidon, we're suffering from this effect. I would like to add one more observational piece of evidence that accretion efficiencies are higher, and it's work led by Kyle Rocha, and I don't know if Kyle is here. There he is back there. But B X-ray binaries, Kyle has presented work where we can reproduce orbital periods, we can reproduce spin periods, compact object masses, but we cannot reproduce companion masses. So the B star masses in the models are way lower mass than what we observe. And if the accretion efficiencies were higher, but you're also still spinning up the star, so you're not preventing it from being spun up, then you could fit the B star masses. So I think work in this direction would actually solve that, but clearly the observations are telling us this is a problem. Thank you.
I think we referred to his paper in our paper. I just didn't have time to show it. Yeah. Thank you.
Linha?
Thank you. Very nice talk. Linha Ma from KITP. I'm wondering if your result is sensitive to the wind physics that you assume for the star. For example, if you're a helium star, when you observe it, it's probably already lose some mass through winds, right?
Right. Since most of these systems are case B mass transfer, and they're not that high mass, any wind relation would have come from the main sequence, but these winds are not very strong at that stage, so we don't expect there to be a strong mass wind dependence.
Okay, thank you.
Ilya Mandel?
So I noticed that one of the things you were comparing with was this factor of 10 accretion efficiency. So Mike Lau has done some work, it's the so-called Hamstars paper, where he actually showed that the accretion efficiency is sensitive to the mass of the accretor in a very strong way, where it's less than a factor of 10 for high mass accretors and much more by 2 orders of magnitude for low mass accretors. And so I'm not saying that this would solve the problem. In fact, it doesn't solve the problem for BX3 binaries, for example. We already looked at that, but it might help at least for some of the systems that you're looking at where the accretors are somewhat lower in mass.
Right, I agree. A detailed evaluation or simulations of the accreting star, how it responds to mass would be very useful.
Okay. Last quick question from Norbert.
Yeah, so very interesting results, Thibault, that you find the mass transfer efficiencies be higher than what's allowed from the thermal accretion model means that if you would do stellar evolution calculations with accretion efficiencies you propose, the stars would come into contact. And they would evolve in a common envelope. So something should happen in these systems, which probably is not in the simple approach which you assume. So I guess we have to move on and find an answer to what actually happens there.
Right. We're not necessarily sure that they accrete faster than the thermal timescale. It's just in tension with the allowed ranges, yeah. So it could still be below. It depends where in the initial mass ratio, initial period the systems have.
Okay, let's thank
We can discuss it.
Thibault again